Introduction to Programming Languages. What is a programming paradigm? It is a style of programming, a way of thinking about software construction. A programming paradigm does not refer to a specific language but rather to a methodology, a particular way to approach programming. Let's dive into the three programming paradigms that interest us today. Procedural programming, also known as inline programming, takes a top-down approach. It involves writing a sequence of instructions to tell the computer what to do step by step. This paradigm relies on procedures or routines, which are blocks of code designed to perform specific tasks. Object-oriented programming focuses on encapsulating data and behavior into objects. An OOP application is built using a collection of objects, each of which knows how to perform certain actions and how to interact with other elements of the application. For example, an object could be a person. That person would have a name that would be a property of the object, and would know how to walk that would be a method. In this paradigm, a method in OOP can be considered similar to a procedure in IP, but it belongs to a specific object. Another important concept in OOP is the class, which serves as a blueprint for creating objects. Functional programming emphasizes passing data through a series of functions to achieve a result. In F, functions are treated as data, meaning they can be passed as parameters, returned from other functions, and combined to create new functions. Functions in F are required to be pure, meaning they avoid shared state, side effects, and rely on immutable data. A pure function is one that, given the same input, will always return the same output, independent of any external state. Shared state, on the other hand, is a state that is accessible by multiple functions or data structures. Managing shared state adds complexity and reduces modularity, making it harder to understand and maintain code. Programming languages. The tools we use to communicate with computers are intricate systems with their own rules and structures. To effectively harness their power, we must understand the fundamental concepts of syntax and semantics. Syntax governs the structure of a program, akin to grammar in human language, while semantics defines the meaning of these structures. By grasping these concepts, we can write programs that are not only syntactically correct but also logically sound. In the field of linguistics, Noam Chomsky's famous counterexample illustrates the complexity of syntax and semantics. The sentence "colorless green ideas sleep furiously" is syntactically well formed, with ideas as the noun, sleep as the verb, and furiously as an adverb. These are all modifiers that form a noun phrase. However, the sentence's meaning is unclear. For instance, what does it mean for an idea to sleep? This difficulty in interpretation is evident even when trying to visualize the sentence "How do you represent colorless green ideas that sleep furiously?" This challenge is not limited to natural language. In computer programming languages like Python, we encounter similar notions. For example, adding two numbers with one, or concatenating two strings with hello world yields expected results. However, attempting to add an integer to a string, like one hello, does make sense and will cause a runtime error in Python. The interpreter, unable to process the command, essentially throws up its hands and says, "I don't know." When programming, it's crucial to avoid these kinds of semantic errors. Consider a few program fragments: 2 evaluates correctly to 4, but Mars Earth 1 causes an error because Earth is undefined. Similarly, adding an integer to a string like Mars 2 results in another error because addition isn't defined between these types. To ensure that our programs run correctly, especially when writing an interpreter for JavaScript in Atmel, we need to distinguish between well-formed and erroneous programs. This process, known as type checking or semantic analysis, involves examining a program's source code to determine if it's well-behaved. This concept extends to natural language as well, where words like execute have different meanings depending on the context. In English and Greek, solipsis, a form of wordplay, exploits this semantic incongruity. For example, the phrase "she made no reply up her mind," and a dash for the door uses the word "made" in different senses, creating a humorous effect. Another example is the line, "She lowered her standards by raising her glass, her courage, her eyes, and his hopes," where lowered and raised are applied to different objects, each with its own meaning. In essence, programming languages, like natural languages, require a nuanced understanding of their structure and meaning. By differentiating between syntax and semantics, we lay the groundwork for constructing reliable and efficient programs. While syntax provides the blueprint, semantics breathes life into the code, ensuring it performs as intended. Just as a grammatically correct sentence can be semantically nonsensical, a syntactically correct program might still produce unexpected results if its semantics are flawed. A deep comprehension of both syntax and semantics is therefore essential for any aspiring programmer.